Hello everyone, and welcome to XY Array. Uh, on this module, it is similar to X-ray, but instead it scans one of three of possible 27 shapes on this diagram here. And trust me, it is very difficult. So in my tutorial, I'm going to cover all of them, but with just one or two examples for each one, because each shape can be scanned from any angle on the module. So as you can see, let's take this one for example. This is the first shape it scans. This is the second shape. This is the third shape. The shapes can, by the way, be there can be two same shapes on one module. So it scans three shapes in the same cyclic order and from the same angles. I mean, each shape it scans from the same angle each time, but on different modules the angle can be different for the same for different shapes. For example, if the module scans these three shapes, it can scan this shape from this angle, this shape from another angle, this shape from another angle, but the angles on the same module each time are repeat for each shape. But yeah, so in this tutorial I divided these shapes in 9 groups, which I'm going to cover. So group of shapes is like, so I divide them so in each group the shapes are similar, and I'm going to partially explain how to identify each one of them. I'm not going to be precise 100% and accurate, and I'm not going to cover all possibilities, just some of them, because there are lots of possible angles the shapes can be scanned from, and at the end the success on this module still relies on a huge ton of practice and your ability to imagine how the scan works. So the first group I divided. The first group is this. So it's basically it's first and second groups. First, second, and third groups are simple. These are shapes with basically curves. First one is the simplest one. We have a sphere and two spheroids. Sphere, the simplest one, basically a unicorn. It's just expanding and basically expanding circle, and then it goes back into void. Very simple. Second one is where is it? Second one is this is plate spheroid. This one. So on these two modules we have Oblate and Prolate spheroid. Plate is this long spheroid. Oblate is this thick spheroid, I'd like to call it. So basically, the way you identify them, if you are lucky enough and the scan does not go somewhere from the diagonal point, like somewhere here or somewhere here, basically on this this one you can see that the So this one, you can see that the section is a small circle, and it basically barely moves across the screen, which means it has to be plate spheroid, because on a plate spheroid, the symmetrical, the circle section in the center is wide, and if it wasn't if it was scanning somewhere from different perspective, it would not be close to circle shape. But in case of prolate spheroid, it's basically the scan happens almost at the pole here, so it goes somewhere like in this direction, so it's almost a circle. In case of plate spheroid, you can see here this is an oval, which basically can mean that it can be both a plate and prolate spheroid, because it's basically scans somewhere from the side, because it's not a circle. But the way in this case you identify it is by the time it takes to scan the thing. So on a plate spheroid, if you scan it from the side, is thinner, which means the time that the oval would take to fade and out and in, so fade in and out, would be less than the time it would take the section of oval, the oval section on a plate spheroid. In this case, it takes quite some time to scan. In case of prolate spheroid, it would be less time. So yeah, this takes some time, which means this is a plate spheroid. I don't have an example of prolate spheroid going from the side, but as I said, I'm not going to cover every possible thing here, because it would take so much time. Okay. Okay, now we're into the second group, which is cones. We have normal cone, bicone or bicone, I don't know, and spherical cone. So the distinct characterization of these three shapes is, well, a cone, and usually they have one distinct line and everything else is curves. By distinct line, I mean in the section. So yeah, let's see some example. So in case of spherical cone, we have a normal cone and a part of a sphere. So in this case, the easy one is scanned from the side, somewhere from the side. So the thing will be horizontal. Well, not it actually, but you understand what I mean. So on this we have, this is the cone that is expanding and then so fading in and then out. And on the right we have a part of the sphere right here, and the curve, the line that divides the cone and sphere is right here, which is basically the where the circle, where the circle is. If we look at a different angle on this one, I believe, yeah, right here, it scans from the bottom somewhere, but not entirely, somewhere from here. As you can see, it starts off with a circle, expanding circle. Actually, it starts with a circle, then there is this line from the section where the circle is, so this one, and then it has this fading out, so fading out circle, which basically means that the thing goes up and the section of this almost a circle is becoming smaller. So let me erase this. How do I erase this? Okay, never mind. So we have a cone here, and when it goes up, the section looks like this, which is almost a circle but an oval, which in our case is indeed what we have. So an oval that becomes smaller. And if it's a spherical cone, and so if it's a spherical cone, as in our case, and the section is somewhere in the middle, we have a part of the oval and a part of the sphere, which would look like something like this, as in our example. So this is wider, this is not wider. Yeah, this is the wider part, this is the, so basically it how do I say this? So the parts kind of, so this line kind of divides into two curves, and the curves themselves, like one of them becomes bigger, one of them becomes smaller. But remember, it started off with a circle because it started somewhere here. In case of Bicone, it's a bit different story. Let's see that those. As I remember, they were here, and okay, I think it was here. Okay, let's see the first one that is simpler. So when it scans from the right, I mean from the side, it looks like this. As you can see, this is the clear line that divides two cones, top and bottom. Let's speed this up. As you can see here, very obvious. In case when we don't have a scanning from the side, it's a bit trickier. So as you can see here, it did not start with a circle, but instead started with expanding oval. Then when it reached like the point where the section crosses this circle, there were two curves, two parts of the ovals, and I drew it here already. When the section crosses, so this is the part of the top cone, this is the part of the bottom cone, and they look like this. And of course, one of them becomes bigger, one of them becomes smaller, and then when the section is completely on one of the cones, it's just an oval that is becoming smaller, or in case if it just started, it becomes bigger until it reaches this circular section, this one, and becomes like this. So yeah, this one has a circle when it starts from here, sorry, here circle at the beginning, and this one has an oval that is quickly expanding. Or in case if it was, in case of if the scanning started perfectly on top or the bottom, or almost perfectly, it would just be gradually expanding oval or close to circle oval. Yeah. In case of a normal cone, it basically has a straight line. If it's scanned from most of the angles, yeah, if it's scanned somewhere from so in case of a cone, it always has a line, as I said, and when it goes from the side, it has a line in the section always, and the rest is just a part of an oval. At some point, the circle the scan can pass the circle, and the rest of the scan will just display an oval, as I said before. Fading out into this point. So if the scan happens somewhere from the top, it's just going to be the other way around. So starting with a quick expanding, or not quick if it's right from the top. So expanding circle, oval, and then a line should appear if the scan goes from this side. So at some point the line should appear. But yeah, so yeah, in our case it scans from the side, and as you can see, it has a line on the bottom, and this expanding and then fading, so expanding and then getting smaller, kind of parabola. That's it for this group. Okay, now we're going to look at the third group, which is normal cylinder, Bicylinder, and spherical wedge. A wedge, I don't know how you pronounce it. So Bicylinder looks like this. It's basically intersection of two cylinders, like this. You can see that they have kind of circular sections. And so basically they're well, this is how you get it. And spherical wedge is just a sphere without two. So basically, if it was just a sphere and you cut off two pieces of it, they would end up being like connected to each other, those resulting sections. Okay, so let's start with cylinder. Okay, there are two ways the cylinder can be sectioned. If the angle is small enough, then the section would start with something like this. Then it would go into an oval, and then it will go to the same thing as the start, but the line is on the other side. And if the angle is big enough, so the section would be like that, for example. So angle big enough that the second line appears before the first line is gone. And it would look like two lines opposite each other, but one of them is increasing, the other one is becoming smaller, the other one becomes larger at some point. And then, yeah, it's in the center. Of course, it will start with the same way, because, yeah, this is how it starts. Start the same way, but in the middle, it's not an oval, it's, well, not exactly oval, but think close to oval. In the middle, it's like that, as we can see on this example here. As you can see, the line is here, then it became kind of an oval. The second line appeared, the first one was shrinking, the second one first was expanding, then shrinking, then the second one was first expanding and shrinking, and between them there were two like these curves. And this, we can see the example of the first one. You can see, I think close to an oval. In this case, it was almost a circle, which means the angle is almost at the scanner goes almost at the top. Yeah, like that. First it goes this, then this, then this. Okay, that's it for cylinder. Let's take a look at spherical wedge. So, how do I draw it? Okay, I'll be back right in a moment. Something like that. So, for spherical wedge, it's going to be always two lines, like that. So you can see at first there were no lines, which means the scanner came somewhere where the section is not present. So first, I think it was somewhere from the bottom. So first it came somewhere where the section is just a circle. Then the section, got to this part. So two of the parts became lines. Depending on how close the scanner is to the bottom pole, the lines will be angled. So if these lines are parallel, that means the scanner came from the very bottom. And if they're angled, that means it was kind of not from the bottom. And you can see, the more it goes on top, the smaller the section became. Like this. Well, smaller it became. Because here everything is smaller. Like this, it became smaller until it fades out. If it's from a different perspective, like here, for example, here it goes straight from the side, so its section just like this. So as it goes to the left or to the right, doesn't matter, this line becomes higher and higher. and section becomes bigger until it reaches this part where the line goes, where the section starts to cross in this circle, and as you could see, it goes back down. Oop, and then back down. So something like here, and then so it becomes higher, and then goes back again. And these are two basic perspectives. I'm not able to show more. Well, the other one would be complex. What else can I show? Oh, from the front, for example. I guess that I showed it already. But if we're starting from the front, it's going to look something like this. Yeah. These things become wider and closer to each other because this section this line right here becomes smaller. Yep. And if you go from the bottom, it's just the same thing as, sorry, if you go from the top, it's just the same thing as from the bottom, but reversed. So first, this will expand with two lines, yeah. Now let's go to Bicylinder, which I'm going to take some time to draw here because it's difficult. Okay, looking good. So, I have my two bicylinders here. Okay. As you can see, two lines appeared on the left and on the right. That's a bit different from spherical wedge. If you look, wait a second. Okay, so if we look from this side, the section is going to be two straight lines that connect these lines, right, these circular sections right here, because it's a part of a cylinder, as you can see, and yeah, right here. And on this part, we're going to connect them like this, and basically we have something like this. Two lines with two circular parts on the sides. They're going to be different sizes because this camera might go from a small angle. So basically, first these lines will be close to each other and they will be long, and then they will be shrinking and getting away from each other, as you can see on the module. Then it repeats, but from the other side, in reverse order, as you can see on the module, like that. And yeah, and if it is from a bit from the angle, the starting bit is going to be a bit different because at first the section might not get to both sides of the bicylinder. So if the start is just going to be something like this, for example, and then a bit later, when it reaches one of the sections of this circle, one of these circles here, is going to be like this and this. So basically two parts of the two different parts of different ovals, with one of them being circular, I guess. You can see on the module right at the end. One of them is still circular, the other one is looks like a part of an oval. Okay, another one which is not in the case of this module, which is not shown here, is when we're going from top, for example. So we're going to have something like here, which is going to be kind of a square, but with sides a bit curvier. And it's going to expand. Another one is when you go right from this angle. Sorry, not this angle, but rather horizontally this angle, but vertically not 0. So basically somewhere from here. So we are going to get something like this. First is going to be similar to other cases, something like this, but in the center you are going to have 4 different how do I if we're going from this angle, in the center your section will cross this circle in these points and these points. This point is did not pass this circular section yet, but this point did, which will result in a shape which has 4 curves, and they're all connected they're connected not in a straight angle. By straight I mean 180 degrees. They're going to be a bit like, let me redraw this. Something like this. Something like this. And when this dot starts to pass, it will happen. So this thing will have 4 curves after this dot passes this circular shape, and it will turn into these 3 dots, as you can see here, these 2 curves. And as the scanner progresses through, these 2 dots will go this way, and basically at some point, the closer this dot gets here, the closer these dots get here. So we will get something like this when this dot is closer to here and this is farther, and it will become a normal shape with 2 curves after this dot passes this section. The same thing as it started with, as I said, when this dot hasn't passed this circle yet. So yeah, it's just like this and this again. Not exactly this, and then this. But at the start this thing expands and at the end it shrinks. And I think I covered as many perspectives as I could. So let's get to the next group. Okay, now it's time for the 4th group, But before we do that, I need to introduce you to two new methods, because we ran out of shapes with curvy sides, and the rest have only plain sides, and it will be difficult to identify them without new methods. Well, very difficult, almost impossible. So the two methods are, they don't always work, but most of the time, and require a lot of practice, and I will speed down everything, because it's a practice after all. So you have, imagine you have a shape, this one. Actually, not this one. Imagine you have a shape. Let's take this one. Only draw this side. So we have this, 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 and this. The thing is, you can, at the very start of the scanning, look up how many sides the shape has. So in case if everything is alright, and the scanner does not go perpendicular to the closest side to it, it will go through one vertex only, and it will only reach some other second vertex in a period of time, in such a long period of time that you will be able to identify the shape. So if it goes, for example, here, and you see a section like this at the very beginning, you can count the number of sides. It will be equal to the number of lines that the vertex is connected to. But in case if the scanner goes perpendicular to one of the sides, so like that, it will immediately go through several vertices, and you won't be able to identify because of how quick it happened. So it just be milliseconds between the scanner goes through these two vertices. Or it can go through a line, through a certain line, like this, for example, and it will have a shape like this. But if you notice that the shape is almost the same, and it only went through one vertex, you can look up it and count the number of sides, which is equal to number of lines, and the number of lines helps you a lot while finding the shape. Another method is tracking a certain side. So for example, the section is here. With time going, it will go here, then here. So basically, these dots, which on the section are going into the same line, eventually will change their direction or split up. For example, when this dot reaches this vertex, it will split up and go in the direction of other lines. So if you see that happening, Okay, I'll draw it a bit differently. So if you see that happening, so this line goes here, this line goes here, and they eventually will meet up. So starting from this vertex, if it goes here, and the second, these two, it goes here, this one goes here, and when this thing reaches the vertex on the actual shape, it will change its direction, and eventually they will all meet, and that's how you find the shape. You just count the number of times the vertex on the section changed its direction. In case of a square, it's going to change, well, twice and then meet up. So when here change direction somewhere, this change direction somewhere, and then they meet up on the section. In case of a pentagon, it goes here, then here, then here, and one of them then goes to the other one, and they meet up. There are only triangles, rhombuses, well, or squares or whatever, and pentagons on these shapes. Yeah, they can only have 3 sides, 4 sides, or 5 sides on these shapes. So let's see this on example, because it's quite difficult to understand. Let's start with this one. Okay, let's try counting the number of lines at the beginning or the ending sections. Now, it appeared quickly, and at the end it disappeared too quickly. And basically this is 0.5 speed, but at full speed you won't be able to see, if it's so quickly, you won't be able to see the number of sides, which means you got unlucky and the scanner quickly passed through one of the lines or the whole side. Oh, and forgot to tell, since we're looking at the fourth group of these two shapes, Rhombic Triacontahedron, which is this one, and Icosidodecahedron, which is this one. One of the ways you identify them is by number of breaking vertices. So they have a lot of sides, and if you see a lot of stuff going on the screen, this means probably one of the shapes, but it's not a reliable way. Instead, you can for this one you can count the number of you can find what the shapes are, because this is the only shape out of all these that has only pentagons and triangles, and all of the vertices have four lines connected to them. So if we look at one of the sides, let's see. Okay, let's look at this one. It went here, then here, which means it's a triangle. In case you didn't see that, let's do that again in a moment. Okay, let's see this shape. The first, it splits into two vertices. First one goes here. The second one went here and returned to the first one, and they connected. So that means there was the one vertex, it went here, the second one, they split, second one went here, then came back here, and formed a triangle. So we have a triangle. Now let's look for something else. Okay, this vertex split here, and then again those two, they change their path. Basically what happened, there was a vertex, it splits into two. Let's do it again. Vertex here, here, then this one goes here, this one goes here, and then the side disappears. So that means vertex went here, so it splits, goes here, here, then this one goes here, this one goes here, and then the shape, and then the line kind of disappears. So that means one of them quickly went to another one, which formed a pentagon. So this shape has pentagons and triangles, which confirms that this is the shape we're looking at. Now let's take a look at another one. Here. Which only consists of rhombuses. These two are the only shapes here that have vertices that are connected to five lines. So if you find that it has that the starting shape has 5 lines, well, 5 sides. Starting shape, not this one. Bicylinder, by the way. Yeah, this one, as you can see, had 5 sides at the start. So this means this one, or this one. And we can just look at look if it has triangles or rhombuses, because these two only consist of triangles and this only consists of rhombuses. And we need to wait again. Okay. Actually, I believe there are 2 shapes on this module, a specific module that have 5 vertices connected to 5 things. This one and the next one. So let's identify them, actually, as you can see. So let's take a look at this one. Let's see, this shape went here and then came back here. So sorry, this vertex, first one stayed in place, second one went here and here, which means it's a triangle. Let's look at that again. Yeah, let's take a look. This one went here, then came back here. It's a triangle. So the first one after the big cylinder is one of these two, and that's a topic for another time. Let's take a look at the second one. Okay. Well, I missed it. One moment. Okay. Take a look at this one. There was a shape, sorry, vertex. It went one way, then another way, and then both of them kind of changed their direction. Let's see that again. Yep, starting from the beginning. The shape went here, sorry, vertex went here, another one went here, then it changed direction. So it kind of looks like this. and then the other one also changed direction. It went here, which gave us a rhombus. Let's hit it again because I'm not sure. Yep, it started here. Okay, starting here. The first one goes here, second one goes here, then it goes here, and then the first one goes to that. As I draw. Yeah, like that. Okay, that's it for this group. See you in a moment. Welcome back. This is group 5, which will consist of these two shapes. Their name is Icosahedron, this is this one, and this one is called
Gyroelongated square bipyramid.
Thank you. Difference is, as you can see, they both consist of only triangles, and they both have majority of vertices with 5 connections. Except this one has all 5 connected vertices, 5 connections. This one has the vertices with only 4 connections on top and the bottom. The only other one shape with vertices with 5 connections, as you remember from previous groups, is this one. So if you see vertices with 5 connections and the sides are not rhombuses but triangles, so this means it's one of these two. So these two are difficult to differentiate, but one of the methods I will introduce in the next group is counting the number of vertices total. Well, in this case, this one has 10 vertices, I believe. This one has 12, and it doesn't usually work if it's 10 or more because it's very difficult to count. But if you can, go ahead. So yeah. Instead, what you need to do is try to find a vertex with 4 connections only. If you did, good job. If you didn't, well, try to check as many vertices as possible. Maybe you just got unlucky and you didn't find one very quickly. But if you checked as many vertices as you can and you still hasn't found a vertex with 4 connections, that means it's like most likely this shape, unless you missed both of these vertices somehow. Okay, let's start. Okay, on this one, okay, as you can see, ends with a vertex with 5 connections. The sides are triangles. I will not repeat how you find them. I did explain that already. All right, I will. Look here. From here, one of the vertices went that way, another went that way. We will look at that in a moment. From here, one went that way, another one that way, and that way. So they met and form a triangle, which means it's one of these two shapes. Okay, now look at the vertices. I already know where the vertex we need is, but I will do one example. Okay, let's try from the easiest one, from this one. Okay, not okay. Once again, yeah, maybe another one. So this one, you could notice that two of the vertices went this way. Once again, here. This went this way, from here that went that way, met here. After they met, this vertex divided into another three vertices, which went that way, and that way. Which means this vertex has 5 connections. Okay, let's try another one. And I have to wait again. Let's take a look at the top one. Here, you could see 2 vertices went this way. Here, 1, 2, and after they met, they split into 2 vertices, which means there are 4 connections to this vertex, and we confirmed that it's indeed this shape. If you could find the second one, just to confirm that this one was obvious, so I will not do that. Okay, let's move on to another example. So this is the odd one out shape. This shape has 5 connections, as you can see, at the start and at the end. Sorry, a vertex with 5 connections, and these 2 as well. So there are 2 shapes out of these 3 with 5 connections. Both of them don't have rhombuses as their sides. You can confirm that yourself. As this one, I mean, they both have triangles as their sides. Let's start with the one which is the one before the odd one out shape, this one. So let's wait. Okay. Okay, so let's take a look at the top one in a moment. So you look here, you could see that 2 vertices went that way, met, and then here, and one went that way very quickly, the other one slowly went that way, which means there are 4 connections. And we can actually find another one, the second one, and I just missed it. This one, no, not this one, this one. You could see that the center, that when the shape approached like the end of scanning, now this one went slowly that way, and then from 2 other sides there were other 2 vertices from here, one, 2, 3, and then when they connected quickly, the resulting one went quickly that way and the shape disappeared. So we found both these 2 vertices, and we confirmed that's indeed the shape. So let's take a look at the first one now. I mean the first one after the odd one out. So after this one, if you check every, so let's start with the top one. 1, 2, 3, 4, 5. There was one that went very quickly that way. The one that went this way, the other one went this way. Once again, 1, 2, 3, 4, and 5. These two were almost at the same angle. This angle was slow, as you could see. One of them went very quickly. Let's do it once again. 1, 2, 3, 4, 5. Let's take a look at two more vertices. Okay. Now this one. Okay, if you look at this one here, you see that three vertices went that way. 1, 2, 3. So like that. But this is where it gets tricky. If you look at this very slowly, you could see when they connected. One of them obviously went that way. One, two, three, and the other one quickly went that way, which is very easy to miss. That's why you can falsely interpret the number. So that's why I recommend you to try to find always find the second one if you happen to find one vertex with 4 connections. So at this point you could think that this is this shape, but actually not, because that vertex had 5 connections, not 4. Just very unclear and easy to miss. Okay, I guess that's enough. You could confirm that every other vertex has 5 connections if you want. Yeah, that's it for this group. Alright, welcome to group 6. So basically group 6 and 7 are quite similar. They have quite similar shapes, but I split them in 2 groups instead. We will start with the 6th one, which consists of Tetrahedron, which is this one, Octahedron, this one with 8 triangles, Triangular Bipyramid, this one, which actually looks quite weird in the manual. I will draw it instead. So it's basically 2 tetrahedrons, I believe. Like that. Alright. And the last one is Trapezohedron, which is this one. The first one, Tetrahedron, is very easy, and I believe, yeah, it's like second easiest shape to identify in the entire octasphere. Just look at a couple of examples and you will see what I mean. It just changing triangle, very quickly changing triangle like that. These two are trapezohedrons. Once you see it, you will never miss it. No, not this one. Wait. I believe I'm looking at the wrong thing. One moment. Yeah, this one, which basically has a total of 4 vertices. If you somehow don't recognize it, just count the vertices. So it's time to actually learn a new method, which is, as I said, counting vertices. So all of these have something in common. These 3 will consist of triangles, and only triangles, as well as these two, but these obviously have much more triangles, so you actually don't need to compare these two. I mean, yeah, these two have vertices of 5 and 4 connections. This have 3 or 4 connections. So let's take a look. So we looked at Tetrahedron. It has 4 vertices, which you can count. Let's take a look at 3, 3, 3, 3. Let's do that on the other side. One second. Octahedron. Okay. Okay. 1, 2, 3. Okay, I miscounted again. So once again, the vertices where multiple lines meet and split into another lines. So you can count those spots. Okay. Obviously, when it appears, it's 1 vertex, 2, 3, 4, 5, 6. We counted 6 vertices. Let's do it again to confirm. 1, 2, 3, 4, 5, 6. 6 vertices. And you could actually confirm that all of the vertices had 4 connections to them, and all of the shapes were triangles. So that automatically makes it this shape here, octahedron. Let's take a look at another octahedron example. Here. 1, 2, 3, 4, 5, 6. Let's take a look. Let's take a look once again. Look at it. Okay. 1, 2, 3, 4, 5, 6. So 1 when it appears, 2 and 3 when top and left vertices were met. So 1, 2, 3, 4, 5, and 6, just like that. And you could also confirm that all of them were triangles, and the vertices had 4 connections. And one was here. Okay. 1, 2, 3, 4, 5. I believe I miscounted. Okay, this one. Wow, there are 3 of these shapes that look similar. Okay, let's count this one. 1, 2, 3, 4, 5, 6. You could notice that. Okay, let's go back to that shape we just looked at. One, 2, 3, 4, 5, and 6. 6 vertices, all of the sides are triangles, you can confirm that, and all of the vertices have 4 connections. It's octahedron, because it has 6 vertices. And once again, this has 5 vertices, this has 1, 2, 3, 4, 5, 6, 7 vertices, this has 4 vertices. Yeah, let's take a look at another 2 of them. And actually this one is quite obvious without checking anything, because it's an obviously scanning from one of the vertices, so it is kind of just perpendicular to one of the vertices, if you know what I mean. It just goes straight into from one vertex to straight to another vertex, which is on the other side. Well, okay. Let's go to another shape. 1, 2, 3, 4, 5, 6, 7, 8. It has 8 vertices, which is none of the shapes we are looking at right now. So it's from different group, which I believe is one of these two. Okay, it's for another, for the next group. So this one has 5 vertices. Let's count that again. 1, 2, 3, 4, 5. Yep, and it actually can have 4 connections. As you can see from the start, it has 4 connections. It does have 4 connections here, here, here. Actually, I drew that. So these 3 vertices have 4 connections. These 2 have 3 connections. All of them are triangles. So that's how you identify these 3 shapes. Let's go to another one, which I believe is the hardest one out of these 4. That Trapezohedron. Here. Okay, this is Trapezohedron. So there is one thing. It's quite lucky that it exists, because Trapezohedron on the module has a slight defect. As you could see, one of the sides of Trapezohedron has a visual bug. You can see that again in a moment. Here, as you can see here, it is a bit broken, and I believe there are some other shapes which have similar defect, but they're not similar. But I believe they are. I mean, it's very difficult to confuse that shape with this one, as I was told. So most likely, so yeah. Okay, let's count the let's count the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I believe I miscounted. Let's do that again. Should slow that down. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This actually has 10 vertices. Let's do it again. Maybe I count it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Something is weird. Hold on. Okay, I was counting. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I was actually counting the right one twice. So yeah. Once again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there are 10 of them, and you can count. You can actually check that all of the shapes have 4 sides. By the way, when you count the number of vertices, make sure that at the beginning and the end you get the correct number of vertices. It's obviously one when the shape, like when the scan goes like perpendicular to one of the vertices, if you know what I mean. But when instead it goes perpendicular to one of the lines, as I mentioned, like one of the in group 3, I think, I don't know. The scanner gets through both of gets through at least 2 vertices very quickly, which you cannot notice. So instead, it would show some like long shape. I don't know if I can find any at the moment. Okay, let me actually see. So it actually applies to both ending and starting shapes of the scanner. So right here you could see that there was a long shape at the end, something like this. Well, it was quite obvious that yeah, here it was quite obvious because there was plenty of time to see that this vertex disappeared, and then this vertex disappeared, as you can see here. This disappears and then this, but at the start it's usually difficult to see. So if this was a starting instead, you should pay attention. If it's a long shape, then most likely there were 2 vertices that the scanner went through very quickly. Okay, it's actually the shape we need. So let's count. This is trapezoid again. Sorry, not trapezoid. Tetrahedron. Yeah, this one. As you can see, this has a visual bug as well. Yeah, you don't always see the visual bug, I believe, but if you do, that means it's most likely this shape, if you can confirm. So let's count. 1. Oh, yeah, that was 4. That is Tetrahedron. Okay, this one had 10 vertices. Let's count that. This had 4 something. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. That was too quick. I need to count again. 1, 2, 3, 4, 5, 6, 7, 8. Too quick. Come on. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh my god, are you serious? Okay, what do I miss this time? One, 2, 3, 4, 5, 6. This one also changed direction. 7 and 8, 9, 10. Okay, I missed the top one when it changed its direction, so that's the reason. Okay, and let's take a look here. Okay, this was cylinder. 1, 2, 3. Too quick. Once again. All right. One, 2, 3. Damage. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright. And you can also confirm that all of them were 4-sided shapes. Yeah. And that's how you identify shapes from this group. Right. Onto group 7, which will consist of cube, Rhombohedron, and Pentagonal prism. This is cube, this is Rhombohedron, this is Pentagonal prism. Well, to be fair, cube and Rhombohedron, they're very similar, and to really identify them, you need some experience. And the method I provide is not reliable at all, I believe. So let's start with Pentagonal prism. It has 10 vertices and 2 pentagons. So if you count 10 vertices and find 2 pentagons and the rest are just rectangles, then it's this shape, because there are only like 2 other shapes with pentagons, this and this, and they obviously are very different from this one. Okay, so okay. Okay, this one, I believe. Yeah. Okay, this side. Let's actually look at one of the sides. Oh, this one. From here, one of the vertices went here, the one went here. Okay, so what happened next? One, two. Then this one went here. This one went here. One, two, three, four. And went somewhere here, it went here, and they met, which is a pentagon. And to confirm that it's the pentagonal prism, let's look at and try to find a rectangle, not rectangle, but a shape with 4 sides. You know what I mean? So this one, from here, went here, here. Let's see again. From here, it went here, here, and then this went here, and from here it went here, which gives us a shape of 4 sides. Once again, 1, 2, 3, 4. So pentagonal prism is the only shape. Pentagons and rectangles, well, shapes of 4 sides. You know what I mean. You could actually count the number of vertices, which is 10. Well, but that's not necessary for this one, because identifying the sides is more reliable in this case. Because I tried and I couldn't do it for some reason. Okay, let's look at another pentagonal prism. Okay, this one is interesting. Yeah, this one. So what you witnessed is scan went perpendicular to one of the vertical lines. So it went here. Then the section started expanding until it reached this point. It was expanding quite quickly. Then, because these two sides have smaller angle, it started to shrink, but slower than it expanded. And at the end, we had a rectangle that disappeared almost immediately. Quite a rare case, but yeah, here it goes slowly and then it disappears. Okay, that's quite a rare case, which is easy to identify, but because it's rare, it's just there's no point in using other methods in this case. And let's look at the third one, which is here. Yeah. Okay. So this one is interesting. I believe in this case it's easier to count vertices. At the start, as I mentioned in previous group, we have a case where it doesn't go through one of the vertices. The scanner doesn't go through one of the vertices at the beginning, but goes through two instead. So suppose it went through one of the lines, so perpendicular to this line. So the scan would look something like this. Yeah, as you saw, it was a little rectangle. If the shape you're looking at is long, that means it immediately went through two of the vertices. Yeah, you know what I mean. So let's count those two. 2, 3, 4, 5, 6, 7, 8, 9, and 10 at the end. Let's count once again. This time slower. 2, 3, 4, 5, 6, 7, 8, 9, and 10 at the end. So there are a couple of shapes with 10 vertices. Maybe let's find the pentagon. Okay, you can. Where is the pentagon? Okay, I believe the right side at the end was a pentagon. Okay, let's see. Okay, here, those two change direction. Then they change direction here again. So what you witnessed was, at the start, we had two vertices, as I mentioned, that it went through. Then they went here, slightly changed their direction here. So let's see once again. 1, 2, then here they changed direction here and here. Well, I mirrored it, they actually went here. Mirrored it, so they went here. They reach certain point, and then they change direction again until they meet at the end. So obviously we cannot have a shape like this, which means this pentagon is connected to this rectangle by one of the sides, and therefore we found pentagon. Okay, enough with this shape. Let's go to the next one. Okay, for cube and what was it? Rhombohedron. Take a look at the cube first. So they obviously have 8 vertices, and all of the sides are have 4 lines. Okay, it's 1, 3. So this one is cube. Actually, don't really care about the speed. So this is octa something. This is cube. As you can see, you can count the number of vertices and confirm that all of them have 3 connections. What else? We have a cube here. Yeah, like that. This is quite an obvious one. We have a cube here, an obvious one. And we have a cube here. This is Pentagonal prism. This is another obvious cube. So, and let's now take a look at Rhombohedron. So this is Rhombohedron, and this is Rhombohedron. Let's take a look again. Oblate spheroid, I believe. So this is Rhombohedron. So the method I believe works is that when you see, so when the scanner goes diagonally and the section you have looks like a rhombus, if the section goes the same way as it's the same way it's squeezed. So suppose it's squeezed like that. Suppose it was a square and it got squeezed like that. If it goes the same way as it is squeezed, so like that, or for example, well, like that, I believe, then it's probably cube. Otherwise, it's not. So let's take a look here. So it feels a bit incorrect for well, it should go that way, but it goes that way, unless I'm dumb. And the shape feels tilted a bit incorrect. In case of a cube, it goes perfectly the way it's supposed to, as I described. I'm not sure if that's correct way to identify. So there was another example here. Yeah, it was definitely weird for a cube. At least intuitively. So it kind of went. So the scan went weird in a weird direction. I would say it went that way, which is not perpendicular to the sides of the shape. I would say that's why you cannot count it as a cube. Yeah, I would say if it's just, I would say on this one, just trust your intuition. I cannot provide you a reliable method. If it goes in a weird direction, not parallel to the sides of the shape, just assume it's this one. And if it has weird sections, so yeah, I'm sorry about that. Anyway, that's it for group 7. And we're approaching the last two, which I believe are quite difficult. I hope there aren't, but we will see. Welcome back. Now we're going to take a look at 8th group, which consists of Dodecahedron, this one, Rhombicuboctahedron, this one, Rhombic Dodecahedron, this one, and Cuboctahedron, this one. So, starting with the simplest one, Dodecahedron, this one. here. It consists of only, as you can see, it consists of only pentagons, and each vertex has three lines connected to it. So it's easy to identify. You just have to look for, just have to confirm that all vertices have three connections and all the sides are pentagons. Let's just do that. For example, take a look at. Okay, I'm going to slow this down. Okay, the top one. So at some point it went two ways, here, then another two ways. Yeah, here, then here, and then after that the line here quickly disappeared. So it made a pentagon. Just to confirm, we can see what happens next. After this line disappears, it becomes wide again, but it goes the other way. It goes this way, but I'm going to draw it here. It gets wider again. Here. Oh, it went wider these directions quickly. And then just at the end connect it back into one vertex. So we have two connected pentagons. That means this is the only possible shape, because nothing else has two connected pentagons, connected by side, I mean. So that's it for this one. Let's move to the next one. Rhombicuboctahedron. This one. So this one. This one is actually harder. So the thing the other shapes you can confuse it with are this one, possibly this one. No, actually, not this one. And maybe this one. No. Either way, the things you identify it with is you're going. Okay, all of the vertices have four connections. First of all, second of all, you're going to see a lot of squares. And if you find a couple of, and if you see that triangles are very rare on this one, then it's this shape. These two shapes are similar, but these and they both have squares and triangles, and both have only vertices of four connections. But this one has much more squares. On this one, you will see triangles. You will see a lot of triangles, and yeah, and on this one you will mostly see squares. And this one actually has less shapes. It will have less lines in general. So let's just on this one. Oh, and also you can just see. You can sometimes see identify the shape by a couple of squares going a couple of squares in a row. What I mean by that is in a moment. Let's see in a moment. So here on the left, 1 square, 2 square, 3 square. So there was like why does Control Z not work? So there was a line that moved up a bit to the side, then it became kind of diagonal, then again, which means we had like 3 squares in a row. There are a couple of modules that have, well, not squares but rhombuses, like this one. This were just straight up squares. It's not a very reliable way, but it's not usually it usually doesn't work, but sometimes it does. So you can notice there are a lot of squares, only vertices of 4, and we can just confirm it's this one by looking for a triangle here. Okay, here was a triangle. Let's see that again. Yep, there was division, and then they met here. So they started from here, this one went here and here, and from here it went here and they met. That was a triangle. Maybe something else. And by the way, on this one, triangle is connected to 6 squares. Both sides and vertices are connected to 2 squares. On this one, sides are connected to squares, but the vertices are connected to another triangles. Let's look at another one, maybe. This one. Yep. A lot of squares and vertices of 4. By the way, sometimes you might see a shape like hexagon. I don't remember if I mentioned that before, but on this one, let's see, where was that? So here, there was a dot. It's well, vertex. It's split into 2. Then both of them change direction. Then both of them again change direction and meet again. Well, there are no hexagons, so that means there is a triangle, square, and a triangle. This one fits this description, and this one as well. Don't think anything else actually. Yeah. Yeah, don't think anything else can have this pattern. This does. This does not have this pattern. So if you see that pattern, that means it's either of these two. And once again, you can, and for the square you looked at, for this square, you can see if the adjacent is a triangle or it's a square to confirm which one of these you're looking at. Squares on this one are connected to triangles by the sides. On this one, they're this one they're only connected. Well, they can only be connected to triangles. So if you see a pattern like this, if it's this one, then these two are squares as well. If you see that these are also triangles, then it means it's this one. Let's actually confirm that, because why not? I forgot where exactly it was. Okay, square like right here. So we need to see what does this vertex do. So if you pay attention, this vertex, at the end, something comes to it. Just copy it. I just copy it here. At the end, when it splits, something comes from above. Pay attention. This one, something here, something from here came here. Before that, it moved like this. This one goes here. So it went from here here, which means before that, it wasn't connected to this vertex, which means it's a square. We can actually confirm that in a moment. You see at the beginning it also went the same way. From here it went here, which is weird, but okay. So pay attention to this one. It goes here and here. This vertex went here and then it went here. Yeah, and form a square like that. Let's see once again. This vertex right now, here and goes here. Forms a square, and so we got this pattern. You can just confirm that on the bottom there is another square, which confirms this is the shape we're looking at. Okay, now let's go to the next one, which is Rhombic Dodecahedron. It's this one. So the difference is there are vertices of both 4 and 3 connections. All of the sides have are diamonds. There are no triangles. Yeah, and there are relatively less shapes, so it will look not as messy as these two. For example, we have this one here. So this one, first of all, this was the shape of 4, vertex of 4 connections. If we take a look, okay, this vertex right here. Let's wait for it. The vertex here, look for it, is going to have here two lines came there. 2 lines came there, and only 1 line came out. This vertex, 2 came, 1 went away. So this is a line of vertex of 3 connections. The starting vertex has 4 connections, it's obvious. So it eliminates these 2 and a bunch of other possible variants. Yeah. So if you confirm that every shape has 4 sides, then it's the one you're looking for. So can be messed up with, I believe, this one and this one, especially this one, because this only consists of four-sided shapes as well, and there are both 3 and 4 connections. However, I believe this one has 10 vertices in total. Yep. And this one has much more. It's 14. So if this thing has much, they are easy to, well, if it doesn't have, it clearly has more than 10, then it's not that one. So you can also count shape for this one. Let's actually do that and confirm it's not 10. 1, 2, okay, it's actually very hard. Well, it's clearly more than 10, right? Okay. Yeah, just confirm there are no triangles. And the last one, Cuboctahedron, this one. So, here, this one. So, just try to find triangles and squares. So, if we look at the starting point, okay, it went into a huge triangle, I believe. No, not a huge, not a triangle. Sorry. Okay, I need to slow this down because. So it went into a big square. It went these ways, and then those vertices turned and formed a square. Double check what exactly happened. Yes, so they went here, and then those went here. So we're fine, because that was too quickly. And if you look at that vertex, this one, look at what happens after. It splits again into 2. And as you could notice, those two as well turned and formed another square. So basically we have 2 squares connected by vertex. It can be this one, or this one. Well, what you need to do is, for this one, what I do is see what's between those squares on the left and right. Okay, this shape right here. So look at this vertex. What it does. It went here and here. So basically, it splits into 2 lines. First one goes here, second one went here, then this one turned, became a part of the second square, and then they merged and formed a triangle. Yep. Let's see that again. 1, 2, and then this went here. So basically from here went here, here, and then this turned, came here, and basically form a triangle. We can confirm the same thing for the right one. Yeah, from here it went here and here, and this one turned back here and form a triangle. Obviously these are not the correct directions, but because on the module they are a bit different, but I'm just drawing it here so we can have a layout. And now it still can be this one or this one. Now we need to confirm what's on the side, to the side of this triangle, if it's a square or a triangle. Because if it's a square, it's one of these two. If it's a square, it's this one probably, and definitely not this one, because triangles here sorry, if it is a triangle, I'm having a stroke. If it's a triangle, then it can't be either of this. It's going to be probably this one, because triangles here are connected to two squares and another triangle on the side. Yeah, if it was a pattern like this, it would probably be this one. If we have instead a square here, then it's this one. Definitely, because as I said, so this shape has triangles connected to six squares. Both lines and vertices connect triangle to squares. This one, lines connect to squares and vertices connect to triangle. We established that one of the vertices connects triangle to another triangle. So now we need to see what this or this shape is. So either of the sides. And we need to slow this down a lot. So we're going to look at this vertex. It goes two ways, down here and here. So it goes down. Well, for the purpose of the layout, I'll just draw it here. Let's see that again. Splits down and up. The one that goes up eventually connects into a triangle. The one that goes left, we're going to explore. So what does it do? Down, then up again, and about this one. We actually need to see what this one does. So this one eventually turns somewhere. We need to confirm if it turns here or not, somewhere else, to this vertex or to some other vertex. I have troubles with that, so let's look closely. Down, turns, and connects with another vertex. It connected here. The vertex that this one, it was here, changed direction at some point and went down on the module, and on this drawing I will draw it to the left. So they connected here and formed a square. So we So we proved that this is the shape. Whew. Well, I hope this explanation wasn't too scuffed. So I'll see you in the next 9th group, last one before some actual solve examples. Welcome back to group 9, last one. So here we have the Herschel enneahedron, this one on the top left, Gyrobifastigium, I guess, this one, and Rhombo-triangular dodecahedron, this one. So these three are quite quirky. By quirky I mean not quirky at all, because they don't really have any features you can easily use to identify them. However, yeah, they're probably the most difficult ones, except this one. This is actually easy. So let's start with this one actually. The second one is located somewhere here, for example. Yeah, this one and this one, these two. Let's start the one which comes after this shape. This one. So to identify it, you can count the number of vertices in this shape. It's 8. And to differentiate, you can also count how many vertices have 4 connections and 3 connections. The other shapes that have 8 vertices are only, well, cube and this thing. So if you can find any, you can confirm that the shape has 8 vertices and there are both vertices with 3 connections and 4 connections among them, then you can confirm it's this shape. Well, let's actually do that. Let's count the number of vertices first. Okay, starting with the 2 vertices that appeared at the beginning, here and here. Actually, let's make it slower so it's easier to explain. One, 2, 3, 4, 5, 6, 7. Okay, counted 7. Let's count again. Maybe I missed some. One, 2, 3, 4, 5, 6. Okay, 7 again. I missed something definitely. Okay, I looked closely and I saw what I missed. 1, 2, 3, 4, 5, 6, 7, and finally 8. Among them, we can see this one has 4 connections. Okay, the one that we finish on also has 4 connections. What else? Okay, this one, for example, has 3 connections. Because Okay, this one goes here, this one goes here, and then the last one. And then when they connected, there was only one that went this way. Okay, okay. Actually, if I'm not mistaken, if you found out that the shape has 8 vertices, well, both cube and this thing have only vertices with 3 connections. So if you found actually any vertex with 4 connections on the shape, that means it's this one. Well, as I said at the beginning, we found the one you finish on is a vertex with 4 connections, which means it's the shape we're looking at. Yeah, this one. Okay, next one. Let's count the number of shapes. Okay, vertices. Okay, it started with 2 again. One, 2, 3, 4, 5, 6, 7, and finally 8. Let's do that again. One, 2, 3, 4, 5, 6, 7, and 8. Okay, and to confirm, let's find any vertex with 4 connections. Yeah, actually the last one has 4 connections, so that is indeed the shape. Okay, let's go to the next one. Next one is this one. It's called Herschel enneahedron. Where is it located? It's located here. Okay, remember I mentioned that this shape here has a visual bug. Well, this shape also has a visual bug, which you can witness sometimes, but not always. Here is this visual bug that you could witness. There was a kind of broken side. Let's see that again. Here, it went down. The problem is these two are very similar, and they both only consist of shapes of 4 sides. They have a very similar number of vertices. This one has 11, this one has 10. And they both have, well, the visual bug. So I personally do not know how to differentiate these two. Rather than counting the number of vertices on this one, or counting the number of vertices of 3 connections and 4 connections. This one has only 2 vertices that have connections of 4. This one has, well, 1, 2, 3, yeah, it has 3 vertices with connections of 4. So if you manage to find 3 vertices with 4 connections, then that means it's this one. Or if you are lucky enough and you can count in this example to 11, then if you can count all 11 vertices and there are no triangles, this shape has no triangles. The other one, this one, has 11 vertices as well, but it does have triangles. So if you can count 11 vertices and there are no triangles, then it's this one. If you can't count 11 because it's, well, the shape is being scanned too inconveniently, or it's just too much for you. For me, 10 or more, counting a number of vertices when it's 10 or more is almost impossible on full speed. Yeah, so only thing that I can try is count the number of vertices of 4, so let's do that. The first one had 4 vertices because it started as a rectangle. One, 2, 3, 4. The top one had 4 vertices because 2 lines went that way and 2 lines went from that way. So they connected and then they went the other way. So that's 2. To find the third one. One. Nope. I actually found the last one. It's actually the one it's finished on. If you pay close attention, it finishes on a trapezoid, not on a triangle. And 1 and 2 and 3 and 4. There are 4 ways that the shape that the lines go to the finishing point. 1, 2, 3, and 4. Yep, that's the third one. So let's look on another one, which is here. No. Okay, that one. What can we see? On this example, it's actually maybe easier to count the actual vertices when it's symmetrical like that. But that won't help. Also, this one does not have the visual bug. So if you make a mistake, oh, actually, never mind. Okay, let's try to find the vertices with 4 connections. I found 2 of them, and they're quite sneaky. Okay, the scan is symmetrical, so they're on opposite sides. Let's take a look at this one. One goes here, second goes here. After they connect, one went here, another one went here. So it was like somewhere like that. And then this one quickly went here, and this one went somewhere here. The same actually happened on the other side. Over here, let's take a look. This one. 1, 2, 3, and 4. So that's 2. Is there a third one, which is very difficult to see? I found it. Not that hard to find. So at the start, here, when these 2 lines quickly went here, met here, and then went this ways, I believe. Hop, hop, yeah. So when the whole thing just appeared, they went here, and then this went the opposite ways. One and two and three and four. Okay. So this is the shape we're looking at. Of course, you need to confirm that. Well, it optionally confirms that there are around 11 vertices, just to make sure, because you know, maybe something else, but if you confirm it's somewhere around 11, then you don't have to worry about other shapes. Yeah. Because if there are exactly 3 vertices, 4 connections, then I believe there might be other shapes that can fit. Actually, no, I think that confirming that there are exactly 3 vertices of 4, the rest of vertices of 3 is probably enough to identify this exact shape. And if you even see the visual bug, then if it's 3, that means it's this one. If it's 2, that means it's this one. Vertices of 4, I mean. Okay, now let's go to the last one. The third one, okay. This one. Okay, so this one also has 11 vertices, as well as this one, but it has most of the vertices with 4 connections, and only 2 vertices with connections of 3, top and bottom ones. You can see there are 6 triangles forming, well, 6 triangles in a circle, and on top and bottom there are like 6 squares. Yeah, if you basically can once again count the approximate number of vertices and find out how many of them exactly are have 3 connections, then you can confirm that this is the shape you're looking for. Okay, we can start probably by maybe evaluating how many vertices there are. One, two, three, four, 5, 6, 7, 8, 9, around 9 or more. That's probably enough. Okay, 9 plus, somewhere around that. Now what can we find for each vertex? What the connections are? Okay, that's not the shape. This one is 4. This one was 3, I think. I need to double check. This one. I believe it was 3 connections. One, 2, 3. Yes, it was 3 connections. One from this side, one from that side. When they connected, it went this way. Okay. Anything else? I believe this one, if I'm not mistaken. 1, 2, 3. Yeah, I believe that's it. I need to confirm. 1, 2, and 3. Yep, 1, 2, and 3. Okay. However, are there any more? This is 4. Oh, this seems to be also 3. I think I made a mistake somewhere. I need to pay closer attention. I found out what's the problem. 2 of the 3 I found are actually imposters. Because if you pay closer attention here, look here. Hop, one of these went down, which means the top one, which I was looking at last time, and the bottom one had one extra action to them. So this one first. 1, 2, 3, and 4. So for the bottom one, that's gonna take a while. This one. 1, 2, 3, and then 4. So it was actually, for the bottom one, it was actually this very quick, this one, and then they connected and went this way. So those two are not true. For now, I actually only found one. Which is this one. It seems safe. I believe that's enough, because, well, if it's around, if you evaluated the number of vertices and it's around 10, 11, and most of the vertices have connections of 4 and only a few, and you at least have found one of them which has connections of 3, that means it's this shape, because these two have mostly vertices with connections of 3. It has mostly vertices with connections of 4. So if you see that most of these vertices have connections of 4, that means that is the shape, in case the number of vertices is around 10, 11. Unless you can count them precisely, which I can't. Yeah. And as well, you can just confirm that there are both sides triangles and sides with 4 sides. Shapes, I mean, with 4 sides. Yep. Maybe one more example, which was located on one of these. If I remember which one. Okay. It's this one. The other two have too many vertices, which is clearly visible. Okay, so let's count approximate number of vertices. And we'll have to wait again. One, 2, 3, 4, 5, 6, 7, 8, 9, and yeah, it's 9 plus. And I could see that it's not not as much as on the shapes before. Okay, Let's see if there are any vertices with 3 connections. Maybe this one? It seems that it had only 3 connections. One, two, three. Yeah, seems like it. Once again. Hope there are no imposters on that one. One from the left, one from the right, and then it goes bottom. Yeah. The rest seem to be all have 4 connections. This one has 4. The last one it finishes on also has 4. This one seems to have 3. Unless I'm dumb, I need to check that. It seems to have 3. It starts off with one line going down and then splits into 2. One, two, three. Yeah, seems like it also has 3 connections. Okay, but let's confirm there are actually more 4 vertices with 4 connections. Let's take this for example. Yeah, this one had 4 connections because yeah. One, two, three, 4. This one went here, then from the top went one, then the slow one reversed its. I'll draw that better. I'll better draw that. 1, 2, 3, 4. 1, 2, then it's reversed direction 4. Okay, anything else to confirm? This one. That was clearly a 4 connected vertices. A vertex with 4 connections. 1, 2, 3, 4. 1, 2, and basically almost the same directions. 3, 4. Yeah. There are 4 or more vertices with 4 connections, which means it can't be this shape nor this shape. They have vertices, maximum 3 vertices with 4 connections, and we found 4. And we also found that there are vertices, at least 2 vertices with 2 connections, with 3 connections. Well, we can't find more because there are not more than 2 of them in this shape. And we confirmed that there are 9 plus vertices. Well, there are actually more because I clearly missed some when I counted. And we also can confirm that it's not the number of vertices isn't too big compared like to these shapes. Maybe we can't confirm, but that's just how you can evaluate it with your eyes. Yep, I hope that wasn't too scuffed, but I believe that's it with all the shapes. Next one, for the next time, I'm going to show how we actually solve the module and maybe do 2 examples or 1, I don't know, where I try to find myself all the shapes without actually preparing for the recording. See you in the next clip. Okay, now we can actually solve one. So we have some interesting shapes. First one seems easy. We can count the number of vertices on that. Second one seems to have a vertex of 5 connections. And the third one will probably be problematic. Okay, so what can we say in the first one? One, two, three, four, 5. Seems to have 5 vertices only, which we can confirm in a moment. 1, 2, 3, 4, 5. Yep. Remember, the only shape with 5 vertices is this one. It was easy. Okay, second one has a vertex of 5 and has a lot of sides. It's either this one or one of these. So let's see if it has triangles or freaking rhombuses. Okay. Yep, it has rhombuses. I can see. If we take a look at, for example, this one, it went something like this, then this. Actually, there's a better explanation. I'll slow down to show. Left. So there was basically 2 dots that went this way. Well, they actually went almost to the right, but then they changed their direction to the same side, and then I believe this changed direction again, which means these are rhombuses. Well, they weren't actually changing directions in these specific directions, but I guess you can see what I mean if I show that again. One, 2, 3, 4, 5, 6. So they were going like this, and this, and this. Yeah, something like this. The third one is going to be problematic, I believe. Let's see if I can do this without the PJ thing. Okay, I believe it's maybe one of these. However, no, it's probably not. We need to confirm what. Okay, let's confirm what type of shapes there are. Yeah, there are pentagons. I could see a pentagon. Look here. And that thing was a vertex. It went here, 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 and then they connected. See this again here. 1, 2, 3, 4, 5. There was a pentagon here. The question is, are all the sides pentagons? Because there are 2 possible shapes, this and this. Well, let's see if there are, let's see how many connections the vertices have. This one has vertices with only 3 connections, this one has vertices with only 4 connections. Let's see what the starting one is. I couldn't see what the starting one is, and I couldn't see what the ending was either, so we have to look somewhere on the side. I believe it was 4 connections. If we take a look again here, 1, 2, 3, 4. Two of the vertices, two of the lines went here and then reflected almost to the same direction, which means this is the third one. That went quite easy. Okay, well, how do you actually solve the module? You're going to assign the primary offset to any of the three solids. You can pick any. So basically you can just start your sequence with any of the shapes. However, the sequence has to be in order. So this one was first, the one after that, the one after this was this one, the one after this one was this one, and this one again. So if you pick the, so if you assign a primary asset to this one, then you're going, then the next one with this and this. Just keep the shapes in their order, but you can choose starting position, starting one yourself. So consider the first two numeric digits of the serial number. 26. Yep. If the first is larger than the second, assign the secondary offset to the solid scanned immediately before the primary offset solid. It's not. So otherwise assign the secondary offset to the solid scanned immediately after the primary solid offset. So if we assign primary offset to this shape, rule states to assign the secondary offset to the next shape. But if this rule was true, and if we assign primary offset to this shape, we would have to assign the secondary offset to the shape before, which is this one. Okay, let's start with this one. Apply the primary offset from the center of the larger cube to obtain the first digit. This is where this table comes. So what you do is, starting at the center, you're going to go in the same direction as the primary offset from the center of this big cube, which means you're going to go to this direction from the center, which is front right. So front right. You are now here, and then go again in the direction that the secondary shape is pointing, relatively to the center position of this cube. It's going to be top right back. But on this cube, you're doing that from the position you ended on after the primary offset. So from this position, you're going right up, right, back. Obviously, it does not matter in which direction, in which order you apply these directions. You can go right, up, back, back, up, right. Okay, right, up, back, right, back. We are ending up here. We're going to. This gives us a pair of digits 1, 1, which we can input. Okay, first pair is done. Now we're going to enter two more pairs, but one second. You're going to replace the primary shape with the secondary shape, and replace the secondary shape with the shape unused. No, the other way around. So our second, basically what it says is our secondary shape becomes primary, and our unused shape becomes secondary. So this is now the primary offset, this one. So back again, starting from the center. We applied a pair of digits, now we're back to the center from this point. We're going up, right, back, up, right, back. And then secondary offset is down, right, back. Down, right, back. Yeah. Okay, from this thing, down, right, back. But it gives us a pair of 1, 3. And lastly, we're going to replace our next shape. We're going to make our next shape the primary one, which is the green one, and the shape after it the secondary one. So green offset is going to be first. So again, starting from the center, down, right, back, down, right, back. That's 2. And the blue offset, front, right, gives us 4. So we do 4. Okay, that's one example done. I will probably do another one, but if not, yeah, that's it. Okay, recording the second example. This one, the first digit is going to be bigger than the second, so the submission will be a bit different. Now let's actually read the shapes, which seems to be easy this time. This is literally free, but okay. Okay, let's count the shapes on this pentagon. Pretty sure it's the Pentagon prism. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that just seems like a pentagonal prism that is scanned from top but a bit tilted. Okay, second one seems to be just this one. It's 2 cut circles. I'm pretty sure it's just 2 cut circles. Yeah, and the third one seems to be also easy. Let's just count the shape, the vertices. 1, 2, 3. That's not so easy as I thought. 1, 2, 3, 4, 5, 6, 7, 8, I believe. Maybe more than 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. Okay, 1, 2 starting, 3 and 4 ending. What was on the right? I missed again. Okay, it's once again 2 starting. This is 3, this is 4. But what was on the right after the start? 5, 6. So these two reflected, which is 5, 6. This also reflected 7. And the top right is 8. So once again we have 2 starting, 2 at the end, and between them we had 1, 2, 3, 4. I'm gonna make sure that it is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'll assume that I didn't miss anything. So if I can remember correctly, the only shape with 8 connections is this one. Let's confirm that. Oh, never mind. It can actually be these 2 as well. But let's see if there are any vertices with connections of 4. If there are not, that that means it's either cube or this rotated thing, which is probably not, because of how the shape looks like. Yeah, I believe this one has 4 connections. Let's double check. One, two, three, four. 2 of them went here, and 2 of them returned. 1, 2, 3, 4. Yep, that's definitely this one. Okay, now let's make sure I highlighted them in order. So second prism is the first one, this spherical wedge is second, and this weird thing is third. So now, when the first rule applies, you're going to actually do everything as before, but in reverse order. So the green one, the third one is going to be the primary, second one is secondary, then second one is secondary, first one is primary. Sorry, no. Third primary, second secondary, then second primary, first secondary, then first primary, third secondary. So let's get our pairs. Yeah, first digit is bigger than the second one, so it's the first rule. Yeah. So the primary one is down, back. Secondary is down, front. Gives us 5, 4. Okay, now again from the center. Primary is down, front. Secondary is left, back. It's 5, 3. And primary left, back. And secondary down, back. 3, 1. Well, that's how you solve XY array. Well, how you want to solve XY array. If you, yeah. Thank you for watching, and I hope that. Thank you for watching, and I hope that tutorial helped you a little bit. Goodbye.